all about electrolytes. Now, you have heard of these things because sports drinks replace electrolytes. Well, why are you drinking these things? Why do you need to replace your electrolytes? What is it all about? That's what this lab is all about. If the electrolyte concentration of your blood is too high or too low, you can have a variety of health effects, anything from just nausea to your heart stopping. For example, the potassium level of your bloodstream too high, your heart stops. Too low, your heart stops. That's what Kevorkian took advantage of with his Dr. Death machine. So your goal, this experiment, is to determine whether a compound is a strong electrolyte or a weak electrolyte or a non-electrolyte, or potentially in some cases a cannot be classified because it doesn't follow the rules of what an electrolyte is, which we'll get to on the next slide. Key point is that you are determining whether things are electrolyte or not whether something contains electrolytes or not. As you'll see with the definition of an electrolyte, you have to make it into a solution in order to test it. And so the fact that the solution contains electrolytes or doesn't contain electrolytes isn't what it's all about. Is the compound that you are testing an electrolyte or not? So what is an electrolyte? Here you go. A compound which, when dissolved in water, key 4 words, results in a solution that conducts electricity. How strongly it conducts is going to be what you're observing qualitatively. Does this light bulb, does this conductivity meter indicate that there is a bunch of ions present, or only a few ions present, or no ions present? Because a strong electrolyte is a compound which, when dissolved in water, fully ionizes. Every single thing that you throw in breaks apart into those plus and minus cations and anions. A weak electrolyte will only partially ionize. Some of it, or most of it in most cases, will stay together as the molecule, not break apart into ions. A non-electrolyte doesn't ionize at all, but still dissolves in water. If it doesn't dissolve in water, it can't be classified because it doesn't dissolve in water, and the definition of electrolyte is a compound which, when dissolved in water, will conduct electricity. It conducts electricity because of the presence of mobile ions. You'll test a solid ionic compound and you'll see that it's not going to conduct electricity because the spaces between the little particles of, say, table salt are vastly too large for an electron to hop through. The ions aren't mobile, so you can't get any ion movement to one electrode or the other electrode. So it's just not going to conduct in the solid state, even though the compound is an electrolyte. Okay, the definition is that a compound, when dissolved in water, results in a conductive solution. Okay, testing it as a solid isn't testing whether it's an electrolyte or not. All right, if it doesn't dissolve in water, you can't test it. So it may be an ionic compound that, if it were molten so that the ions could move, magnesium hydroxide, for example, Mylanta, doesn't dissolve in water. That's why you have to shake it if you're taking Mylanta. It doesn't dissolve in water, and so it won't conduct electricity because the ions aren't mobile. They're just being shaken up in the water. They're not breaking apart from each other and being mobile to allow conduction. So how can you determine whether something is going to dissolve in water? What are soluble ionic compounds? Well, here you go. This is the solubility table out of your book. It's a little bit simplified because this presents everything as black and white. And in 152, you'll start talking about how gray this really can be. However, the table can be a little bit confusing in that soluble compounds are ones that are going to be AQ, dissolve in water and form aqueous solutions. Insoluble compounds are the ones that are going to have a S in a reaction after them because they form solids. Okay? The bottom half of this table switches things up. It has insoluble compounds, solids, on the left, and the soluble exceptions on the right. Now, some of the professors that teach 151 will make you memorize this table, and some of them won't. I'm not a big fan of memorization, so I don't encourage my students to. However, if you have to memorize this, and certainly if the MCAT is in your future, you'll need to memorize this, then keep in mind that there are actually not that many rules here, okay? For example, all things that have alkali metals in them or ammonium are soluble, no exceptions. That's the soluble exception down here, right? Carbonates, generally insoluble. Phosphates, chromates, and sulfides are insoluble except for alkali metals and ammonium. That rule, okay? So the exception down here is already the rule up there. So if you need to memorize this, take a breath. When you're making your flashcards, there's not that many cards here to really be made. Okay, so I think I have a question for you here on the next slide. Using that table, and I will put it back up for you, classify rubidium chloride as either soluble in water or insoluble in water. And then based on your classification, decide whether rubidium chloride is a strong, weak, non-electrolyte or unclassified. I will put the table back up so that you can see it. Here we go. Okay, and since rubidium chloride contains an alkali metal, rubidium, it is definitely going to be a soluble ionic compound, and as a soluble ionic compound, it of course is therefore a strong electrolyte. Some other possibilities for things that could be strong electrolytes are strong acids or bases. These are, for the most part, molecular compounds, gas phase molecules that when dissolved in water will fully ionize. Every single HCl molecule that goes into water will fully ionize into H plus and Cl minus. So again, not a big fan of memorization. I'd rather have understanding, but there are only 6 strong acids. The halogen acids, HCl, HBr, and HI, not HF. Okay, HF is a weak acid. HAT and HOG, nobody's gonna ever see those things, so don't even worry about it. Or not OG, what is the last one? TS, tennessine, new elements. Presumably they would be strong acids, but you're not going to ever see those things. So the halogen acids, but not HF, HCl, HBr, HI. Nitric acid, very important industrial compound. Sulfuric acid, but only one of these 2 H's. And perchloric acid. H2SO4 is battery acid, and perchloric acid is another important industrial compound. So just naming-wise, HCl as the gas is hydrogen chloride, and HCl aqueous, that's when it becomes hydrochloric acid. I point this out because nobody ever pointed it out to me, and I was always confused when I was an undergraduate studying chemistry. Strong acids will be strong electrolytes. You're going to put them in water, they're going to conduct strongly. In our experiment, the light bulb will come on brightly. Strong bases are soluble metal hydroxides, which are the alkali metal hydroxides and barium hydroxide, according to your textbook. This is one of those potentially gray things that varies from textbook to textbook. Is it a soluble ionic compound or not? The alkali earth metal hydroxides. What this means for strong acids and strong bases is that the arrow only goes to the right. You throw it in water, it fully ionizes. Every single molecule you throw in fully ionizes to the H plus and the anion. For the bases, it fully ionizes to the cation and the hydroxide ions. Weak acids and bases, on the other hand, do not fully ionize. Notice the arrow goes both directions. The arrow goes both directions. The arrow goes both directions. Okay? Writing these acids, we can write it as H plus as the product side or H3O plus. Technically, the H3O plus is correct. When I took general chemistry, they didn't feel the need to fully explain everything right up front. It's like trying to teach calculus to a first grader. It's just not necessary. H plus was totally fine when I learned it. Technically, it doesn't exist. H plus in water is H3O plus. I leave it to you and your instructor to figure out how you would like to write H plus aqueous. Are you just going to write it that way, or are you going to write it as H3O plus? It doesn't really matter either way. Do keep in mind, though, that if you're going to write it as H3O plus, then you need to have a water on the reactant side. In either case, having this acetic acid, this vinegar, is a 5% solution of acetic acid, as you'll see later in the semester. Acetic acid stays mostly as the unbroken apart, the undissociated, not broken apart, not dissociated. It stays as the molecule. There are not very many ions present. The conductivity is going to be weak. In our experiment, we will see the light bulb only come on weakly. Okay, ammonia, weak base, same thing. Windex, window cleaner, stays mostly as molecules. These both dissolve in water wonderfully. Vinegar dissolves in water pretty much as you could want. Same thing for ammonia. But it doesn't ionize. It ionizes some. An interesting phenomenon that occurs with weak acids and bases is something called the Ostwald dilution law. It's an application of Le Chatelier's principle, which you don't get to until 152 in chapter 14. But bottom line is, if you add more reactant, more water, to the weak acid or weak base, it pushes the reaction more to the right-hand side, and you get more ions. Therefore, diluting a weak acid or a weak base is a nice way to test, is it a weak acid or a weak base, because the conductivity increases. For a strong electrolyte, arrow only pointing to the right, it's already fully ionized. Diluting it doesn't have any effect unless you diluted it to swimming pool size dilution, added a ton of water, and then the conductivity would get less. However, we're not doing that. We're moderately diluting. If you moderately dilute a weak acid, it appears to be getting stronger because there are more ions present. Strong electrolyte won't do that. So here's a question for you. HF, weak acid. You dilute, just testing it with a conductivity apparatus. What are you going to see? Is the light going to turn on brightly for a strong electrolyte? Is it going to turn on dimly for a weak electrolyte? Is it going to not turn on at all for a non-electrolyte? Based on your answer, is the light going to get brighter? Is it going to get dimmer? Or is it going to remain unchanged if you dilute moderately a solution of HF? And of course, HF, being a weak acid, will only have a dim light, and if you dilute it, the light will get brighter. Strong electrolyte, RbCl, you saw above, was a strong electrolyte. If you dilute it, what's going to happen? And the answer is that it will be unchanged because it is already fully ionized. We will perform this lab as a demonstration because this conductivity apparatus can be deadly. You have a bare electrode here and a bare electrode here. In the fire service, we call this a suicide cord. And if you touched both of these at once, you would likely stop your heart. So your instructor will do it for you, dipping these two electrodes into solutions of each of your electrolytes. So if you're writing up your procedure, you would still write it up as usual, but you would note that your instructor performs the experiment as a demonstration. Things to think about theoretically. What does it mean when the light turns on brightly, when there's a strong conductivity? What does it mean when the light turns on dimly, only weak conductivity? What does it mean if the light doesn't turn on at all? And I wrote there, what could it mean? Because maybe there's more than one answer to this question. Think about those things, have fun in the lab, be safe, take good observations, and we'll get ready for the next lab in the next video.